Let's do a related rates problem that involves rotation. So the first thing we always want to do in any related rates problem is always start by reading the problem very carefully. So here's our problem. A convict walks along a straight path in the prison yard at a speed of 6 feet per second. A searchlight is located on the ground 30 feet from the path and is kept focused on the convict as he walks. At what rate is the searchlight rotating when the man is 40 feet from the point on the path closest to the searchlight? Okay, so there's a lot of information in this problem. The second step that you always want to do in a related rates problem is draw a picture of the scenario. So let's draw that picture next, and as we do that, we'll kind of unpack the information that's given to us in this problem. So I already have a picture down here sort of set up. And of course your picture doesn't have to be this detailed. You just want the main features, the important geometric shapes as well. Okay, so we have a convict walking along a straight path in the prison yard at a speed of 6 feet per second. So here's my convict, and he's walking along this path. And we know he's going at a rate of 6 feet per second. Okay, what else do we know? We know a searchlight, okay, so here's my searchlight over here. A searchlight is located on the ground 30 feet from the path. Okay, so that's important, right? The searchlight is 30 feet from the path. Okay, so here's the path and the searchlight, and then the distance between them we know is 30 feet. Okay, so that's always 30 feet. That never changes. Okay, so what else? The searchlight focuses on the convict as he walks, so we kind of see that here with this light beam. At what rate is the searchlight rotating when the man is 40 feet from the point on the path closest to the searchlight? Okay, well, so here's the point on the path closest to the searchlight, right here, the star I'm drawing. So we want to know what rate the searchlight is rotating when the man gets to that. Sorry, that is at the point when he's 40 feet from the point I have marked in a star here. Point. So let's put some variables into our picture here. So what's changing? Well, as the man is walking, this distance here is changing, right? He's getting closer to this this star here. So let's call this distance x. Okay, now what else is changing? Well, the angle of the searchlight is also changing. That's something else we're interested in. So I want to assign a variable to that angle. So I'm going to call that angle theta. Okay, so what have we done so far? Well, we've read the problem carefully, we've drawn a picture, and on that picture we've labeled a few things. So we've labeled things that never change as numbers. So this 30 feet here, the 30 feet never changes, so I labeled that as a number. But then I've labeled things that change as variables. So I have x, which is the distance the convict is along this path, which is changing. And then I have my angle theta, the angle of the spotlight, and that's also changing. Okay, so what should we do next? Let's go ahead and think about what rates we know and what rates we're trying to find. Okay, so what are we given here? Well, we're told that the convict walks along a straight path in the prison yard at a speed of 6 feet per second. Okay, so that's something, right? That's a rate. So which variable in my picture does that correspond to? Well, it's the speed he's walking along the path, so I know it's going to have something to do with x. So DXDT. Okay, so remember, I'm kind of thinking of, and let me draw this in a different color. I'm kind of thinking at this point here is my reference point. The line between the path and the searchlight, that's sort of my reference point, and the convict is walking towards that point. So he's walking towards that point at a speed of 6 feet per second, but we want to think about the sign. Okay, so his speed is 6 feet, but is that positive or negative? So it's going to be negative, and that's because as he walks towards that point, this direction, that distance x is decreasing. So I'm going to say DXDT equals negative 6 feet per second. Okay, what else? What other rates are kind of in this problem? The other thing that's changing is the spotlight. The spotlight is rotating, and what we're actually looking for is the rate at which the spotlight is rotating. So that's the rate of change of the angle theta. So d theta dt is what I'm actually interested in finding ultimately in this problem. So now that we have established our variables and the associated rates of change of those variables, we want to find some sort of relationship between these variables and write an equation to represent that relationship. So here the variables, the important variables in my story are x, the distance that the convict has walked along this path, or the distance he is from my red star here. And then theta is also an important variable. So I need to come up with some sort of relationship between x and theta. So let's look at what we have here. Often it's going to be some sort of geometry formula that's going to prove useful. So I have a triangle here, right? And it's a right triangle. This is a right angle here. And I know two sides of the triangle. One is a variable x, the other is just 30 feet, it's a constant. And then I have this angle, theta. So the relationship that we're going to be able to use here is actually the tangent of the angle theta. So remember, the tangent is the opposite side over the adjacent side. So tangent of theta then would equal x over 30. So this is a relationship between the variables we're interested in. Okay, so now if I look at my equation, before I proceed with the next step, I just want to make sure that I've eliminated any variables from my equation that aren't changing with time. So in other words, I want all the variables in my equation to actually be variables. So theta is a variable, right? The spotlight's rotating, so that angle is changing with time. And x is a variable. The distance the convict is from my red star is changing. Okay, so I'm good. Both of my variables are actually variables. So then the next thing I want to do is take the derivative of this expression. And I want to be careful when I take that derivative. I need to use implicit differentiation because theta and x are actually both functions of time. Theta is a function of time and x is a function of time, right? Because the angle that the spotlight is at depends on the time. It's changing. And also the distance the convict is along that path also changes with time. So I need to remember to use a chain rule and take the derivative implicitly. So let's start on the left-hand side. I need to take the derivative of the tangent of theta. Okay? So actually, first of all, to remind you that we're taking the derivative with respect to time, let me just write ddt of both sides. So ddt of tan theta equals ddt of x over 30. So I'm taking the derivative with respect to time of both sides. All right. Okay, so what's the derivative of tangent? Well, we know it's secant squared. So the derivative of tangent theta is secant squared theta. But because theta is a function of time, I need to multiply by that derivative. So this is going to be times d theta dt. Okay, and then what about on the left-hand side? Well, if I want, I can think of x over 30 as 1/30 times x. So the derivative of that is just going to be 1/30. But once again, because x is a function of time, I have to multiply by its derivative. So it's going to be 1/30 times dx dt. Okay, so this is my derivative relationship. This gives me a relationship between the rate of change of the angle and the rate of change of the convict along the path. All right, so what should we do next? At this point, we can go ahead and plug in any rates that we know from the problem. So for example, if I scroll up a little bit, Remember that we said previously that DXDT was negative 6 feet per second. So that's always true. He's always walking at that speed of 6 feet per second towards the red star. So I can go ahead and plug in now DXDT into this equation. So I'm going to go ahead and do that. So I have secant squared theta d theta dt equals 1/30 times negative 6. Okay, so that's going to give me secant squared theta d theta dt equals negative 6/30. So that's secant squared theta d theta dt equals, and then if I reduce this, I get negative 1/5. Okay, now ultimately, what am I looking to find here? If you remember, ultimately we're looking for d theta dt. So I'm going to go ahead and solve this relationship for d theta dt, which I do just by simply dividing that secant squared to the other side. So d theta dt equals negative 1/5 secant squared theta. Okay, we're really close to being done now. So remember, if I scroll back up here, it asks, at what rate is the searchlight rotating when the man is 40 feet from the point on the path closest to the searchlight? Okay, so here's an important piece of information. We're looking for the rate of change of the angle, specifically at the instant when the man is 40 feet from the red star in my picture. So that is when x equals 40. Now you want to be careful with these particular information or particular moment statements. You never plug in these particular moment pieces of information until this essentially last step. So I'm ready now to plug in this particular moment information. Now this problem is maybe a little tricky because I'm interested in when x equals 40, but if I scroll down to my formula here, there's no x's in my formula. This may be a little alarming to you, but it's okay because if we know that x equals 40, we can use our original triangle relationship to translate that into information about theta. So we're going to work out to the side here for a second, and we're going to take this information when x equals 40 and see how we can translate that information into something we can use to plug into our d theta dt over here. And actually, let's go back to d theta dt over here just for a second. I'm going to rewrite this. Recall that cosine of theta is 1 over the secant of theta. So then I can write this as negative 1/5 times cosine squared theta. Okay, so when x equals 40, what does our triangle look like? So I'm going to have this side of my triangle here, this leg of my triangle, to be 40, and this leg of my triangle is always 30. So then what I should be able to do from this triangle is actually figure out what cosine of theta is, and then I can just plug that value directly into my d theta dt formula over here. Now remember that cosine is the adjacent over the hypotenuse side. So I need to compute what the hypotenuse of this triangle is. We can do that using Pythagorean theorem. 30 squared plus 40 squared should equal my hypotenuse squared. And if you work through the details there, you're going to find that this hypotenuse has a length of 50. So then once we have that piece of information, we can just read off the cosine of theta just directly from our triangle, right? The cosine should be the adjacent side of my angle theta, which here is 30, over the hypotenuse. So that gives me 30/50ths, or if I reduce, 3/5. So now I'm going to come over and plug that into my d theta dt relationship. So I have negative 1/5 and then cosine of theta squared. Okay, so 3/5 quantity squared. So that's going to give me negative 1/5 times 9/25, which is negative 9/125. And this right here is what I'm looking for. This is the rate at which my angle theta is changing. My units here for my angle are going to be radians per second. And in this case, we got a negative value, which makes sense because our angle is getting smaller as this beam follows the contact. Now, there are actually several ways you could have gone about doing this last step. So we used our triangle to solve for cosine theta, and then we plugged cosine theta into this relationship. There are many other similar things you could have done. You could have stuck with this negative 1/5 secant squared of theta and figured out what secant was from the triangle. You could have used the fact that 1 plus tangent squared of theta equals secant squared of theta and solved for tangent in this triangle. Now, then we wouldn't have even had to find the hypotenuse. But anyway, the point is there were several different ways you could have gotten to this point, but this is our d theta dt, which is our final answer for this problem.